Yeah, so we are still continuing together. And I thank you very much, by the way, for being a very good follower of mine. And please, always forward some of these links to some of those groups of yours. If you're a student, please forward them to your friends. If you are a teacher, for you, I say asante sana. Thank you very much. Thank you very much for always following me. I am very, very humbled and grateful. Now, we're just adding on what we have just seen in the most previous video. Now, we have seen, in the previous video, we have seen how the leading strand gets replicated. What about the lagging strand? By the way, why they call it lagging strand? This is why they called it lagging strand. This one you're going to see is why they called it lagging strand. How? Come with me here. Now, when you check here, we are seeing that on the leading strand we saw the primer attaching self here. And then after attaching a self here, then the polymerase coming, starting from there, adding nucleotides, and whatever nucleotides are being added must be automatically running in a 5' 3' direction. And because everything is like that, 5' 3' direction, a direction which is the direction within which DNA polymerase works. That's why this one, the more the helicase opens, the more we add nucleotides, and by the time the helicase reaches here, everything is done. Everything is done. This one has been replicated, has formed a new chain, has formed a new copy. But on this one, things are different. Why are things different? Remember, I've told you that for DNA polymerase to do its work, what is being added, the molecule which is being added must be being added in a 5' to 3' direction. However, when you check on this strand is 5' 3', and this thing is moving this side. So it means if we are to add nucleotides, this nucleotide automatically must be running in a 3' to 5' direction. We'll be moving in 3' to 5' direction. Which means what? It means now, if we are to add here, these nucleotides would be, if we are to add a nucleotide here, this nucleotide will be needing a 3' at the extreme end. So it means the nucleotide here would be like this. We would be having a nucleotide which is like this. We have pentose sugar, you have a pentose sugar, nitrogenous aminophosphoric acid, and nitrogenous base like that. Pentose sugar, we shall have a pentose sugar like that, a nitrogenous phosphoric acid, and a nitrogenous base. Then you need a pentose sugar, nitrogenous phosphoric acid, and then nitrogenous base. So it means automatically, if this is 5', it means the chain which will be added here was supposed to be added, because this will be 3', we were supposed to be adding it in this format, so that we end up having the 3' and the 5', this in that format. However, remember, I have told you that DNA polymerase, for it to do its work, it does its work in a 5' to 3' direction. That means what? That means that this chain that we are adding must be being added. It must be moving. It must be being added in a 5' 3' direction if the DNA polymerase is to do its work. So the question is now, what happens here? Since that is, we are seeing this one is moving 3', 5', if you had for this direction. But we are saying DNA polymerase, for it moves in a 5' to 3' direction. So the question is, how does the polymerase go about that? So how it goes about that is in this way. Here, for the case of the lagging strand, what happens is, since we are going to add a molecule in a 3', 5', and DNA polymerase for it works in a 5', 3' direction. For DNA polymerase, it works in this direction, 5', 3', as it was the case here. You see, we were moving in 5', 3', so that's why everything was okay, because the chain which is being added in a 5', 3'. which is the same direction within which DNA polymerase was working. That's why everything here was okay. Things we are replicating it continuously because the new chain is being added in a 5', 3', which is the same direction within which DNA polymerase works. But here we are seeing opposition. How? We are adding, what we are adding is moving 3', 5' like that. 3', we are adding 3', 5'. And we are saying the DNA polymerase works in 5', 3'. So what happens here is something very simple. And what's that? Instead now, on this case, on the lagging strand, on this lagging strand here, instead of the primer attaching itself at the extreme end here, at this extreme end here, what happens is that in this case, for the case of the lagging strand, the primer comes and attaches itself at different points. Not at the extreme end here. It comes and attaches itself at different points on the lagging strand. How? Some strand comes, some RNA, let me put another, just put another nucleotide here. So some RNA primer comes and attaches itself at this extreme end. It comes and attaches itself here at one point there. Then another primer comes and attaches itself where? Maybe here. After this is a nucleotide, this is a small short RNA, it means it has a nucleotide which can bond with this nucleotide here. So after that, after it has bound with there, it has bound with at that point here. Now remember, what was supposed to be added here was supposed to move in a 5, it was supposed to be moving in a 3' to 5' direction like that. But now what happens here is that in this case, since DNA polymerase must move from 5' to 3', instead of DNA polymerase now moving like this, which is opposite to the direction it's supposed to move, it will move in the other way around. How? I am saying the DNA polymerase in this case now will move from this side to this side. Why? It is trying to maintain that. So we are just continuing from where we had stopped in the previous video. Now, in the previous video, we were able to see that here on the leading strand, it is oriented, it is replicated, continuously. Now, when it comes to the lagging strand, by the way, why is it even called a lagging strand? Why do you think it's also called a lagging strand? Now, here we see that this strand is moving from 5' to 3' direction. Now, it means that if I was to add nucleotides, these nucleotides would be moving. If I was to add another chain here, automatically the chain would be moving in a 3' to 5' direction. Isn't it? Because this is 5', so it will be 3' to 5' direction. However, remember I told you that DNA polymerase, DNA polymerase does its work if it is moving in a 5' to 3' direction. That's why on the leading strand, things were very simple, life was okay. Why? Because the new molecule, the new DNA strand which was being added in a 5' to 3' direction. That's why it was replicated uniformly, because as this one was opening, this one just keeps adding like that, because the new strand is being added in a direction of 5' to 3' direction, which is the direction within which DNA polymerase works. But here, the strand we are going to add, it means if we are to add here, we will be adding a strand which will be in this format, which will be having now the pentose sugar, will be having a pentose sugar, a nitrogenous base, and then a phosphoric acid. A pentose sugar, nitrogenous phosphoric acid, and nitrogenous base. Like that. Now, when you check here, a pentose sugar, nitrogenous, then a phosphoric acid, and a nitrogenous what? A nitrogenous, and then a phosphoric, pentose sugar, phosphoric acid, and nitrogenous base. Now, when you have to look at all these things, you see that in all the things, what you see, when you check, you realize that here, when you check out all these things, you realize that here you have a 3. Of course, if this one is now come and join up together, like it means what will be formed here will be a 3 prime, because you see this is carbon atom number 3. Remember, this is 1, this is 1, 2, 3. And then here this will be 5 carbon. So you see what will be now forming would be what we shall be adding here would be moving in a 3' 5' direction. Mind you, we have said DNA polymerase, for it works if what is being added is moving in a 5', 3' direction. So the question is, how does DNA polymerase work on that? How does it deal with that situation where we are adding a molecule in 3', 5' direction, but for it works in a 5', 3' direction. So how does it do its work? How does it result that? Think about it. This is what happens. Now, on the lagging strand, this lagging strand, what happens is not like how we have seen here. For the case of the leading strand, things are just done very fast. Why? Because this direction within which this molecule we are adding is moving is 5', 3', which is the same direction for the DNA polymerase. But here, what happens is that in this lagging strand, what happens is that in this case, we are not going to what? We are not going to have the primer being formed at the extreme end as we have seen the leading strand. But instead, we are going to have our primer. We shall have our primer being added at different what? At different points. So we shall have one primer there, and one primer here, and one primer there, like at different points there. Still, like the way we are saying on the lagging strand, what happens? On the lagging strand here we are saying, unlike the leading strand, on the lagging strand, different primers, whose synthesis is also catalyzed by RNA primase enzyme. RNA primers attach themselves at different what? At different points. They attach themselves at different points. At different points on the lagging strand. At different points on the lagging strand. They attach themselves at different points. Now, we are saying, after attaching themselves on the different points, after they attach themselves on different points, what happens? Of course, themselves, these primers still are the same like they did last day, the previous day. These ones act as what? They act as initiators. They still act as initiators. Initiators for what? They still act as initiators for protein synthesis. They still act as initiators for DNA replication. How? So it means after they have attached themselves onto one extreme end, of course, this is the RNA which also has nucleotides, some of which are complementary to these bases. So if this one was, of course, guanine, of course, maybe if it was thymine. If this one was guanine, this will be cytosine. If this one, remember this one was the one which was complementary with this. So if this was cytosine, it means this was guanine. If this was thymine, this was adenine. This was thymine. Like that. So we are going to see if this is thymine, this means that this was adenine. So it means after this, like we have described here, after the primer attach itself onto one end of the after the primer attach itself onto one end of the on two different points of the lagging strand, what happens is that our enzyme, which enzyme? DNA what? DNA, our enzyme which was the DNA polymerase. Our enzyme, DNA polymerase still comes. The DNA polymerase still does the work like it did on the previous one. DNA polymerase, again what? Moves along the lagging strand, But now, this time, it will be moving a lagging strand in a direction which is opposite to that of DNA helicase. Why? Because because remember what was supposed to add here was supposed to be running 3 prime to 5 prime direction. But remember, I have told you that this strand, okay, we are saying the strand which is supposed to be added onto the lagging strand automatically must run in a 3 prime to 5 prime direction. But remember, I have told you that the DNA polymerase, for it works in 5 prime. This thing I'm over repeating it for a purpose. DNA polymerase works in a 5 prime, 3 prime direction. Therefore, to maintain that flow of 5 prime, 3 prime direction, to ensure it moves in a direction which is with respect to what is being formed, for it to be able to ensure it moves in a direction of 5 prime, 3 prime direction, it moves in opposite direction, so that it can ensure that instead of moving from here to here, it moves from 5 to 3. That's why we are saying it moves in a direction which is opposite that of the idea of the helicase, because helicase, when you see helicase is moving in a 5 prime when you with respect to the when you look at the DNA at the lagging strand, DNA polymerase is moving in a 5 prime to 3 prime. Is moving in 5 prime to 3 prime. But if you consider the strand which is going to be formed here, if you consider the strand which is going to be formed here, the strand which is going to be formed here on the lagging strand, it will be moving in a 5 prime to 3 prime. So, but for DNA polymerase it must work, it works in a 5 prime to 3 prime direction. So that's why instead of moving like this, which will be now in a 3 prime to 5 prime direction, it will walk in the other opposite direction to ensure that it is moving from 5 prime to 3 prime direction. So what does it mean? It means now here, when you have got a primer being formed here, you will have now nucleotides come and add themselves here. For example, if this was a nitrogenous base, and then you have a pentoid sugar here, you have a phosphoric acid will form there. You have a nitrogenous base, you have a pentoid sugar here, you have a nitrogenous base, and you have phosphoric acid like that. Likewise, you also have pentoid sugar, you have a pentoid sugar, you have a nitrogenous base, you have a phosphoric acid. Then you have for a pentoid sugar, you have a nitrogenous base, you have a phosphoric acid. Yeah, I think I'm drawing them in opposite direction. I'm supposed to be drawing them opposite. I'm supposed to be drawing them in the other in opposite direction. Why? I need to draw them in a way that I am ending with a 3 here, because this is 5, which must be a 3. So if that's the case, then I need to draw them in a direction which is opposite to this. So it means here I'll have a pentoid sugar, I have a phosphoric acid and a nitrogenous base. I have a pentoid sugar, I have a nitrogenous base and a phosphoric acid group. Then I have a pentoid sugar, I have a nitrogenous base and a phosphoric acid group. I have pentoid sugar, I have a nitrogenous base and a phosphoric acid group like that. So we are saying after the primer has attached, now the DNA polymerase moves along the strand. But starting from where? Starting from where the primer is, the DNA polymerase moves starting from where the primer is, moving in a direction which is opposite that of the what? Of DNA helicase. So we are saying DNA polymerase moves along the lagging strand, in opposite direction to that of the DNA helicase. It moves from the primers, starting from the primers, and moves along this attached self. It comes next to the primer, where the primer is here. Then it starts moving in opposite direction this side, in opposite direction that of the helicase. Adding what? What is it doing? Adding DNA what? Adding DNA nucleotide, just like we saw on the leading strand. Adding DNA nucleotides, which are complementary. Following what? Following the complementary base pairing rule, but in a what? In a 5 prime to 3 prime direction. also in a 5' to 3' direction. Why am I saying 5' 3' direction? Yes, the strand is moving in a 3'. Of course, when these two nucleotides come and join, they form peptide bonds. Even here, this one joins here, then after the nucleotide is formed here, they also bond together. So we are saying, yes, the strand is moving in a 5', in 3' to 5' here. This is 3' to 5' here, like that. But we are saying since the DNA polymerase is moving from the primer, coming this side like this, it means, yes, though the molecule which is being added, when you consider how the DNA polymerase is moving, it is moving in a 3' to 5', but for the polymerase to do its work, it does it in a work in a 5', 3'. So that's why the DNA polymerase, for it, when it is adding nucleotide, when it is catalyzing addition of nucleotides, it catalyzes the addition of nucleotides, but when it is moving in a direction which is opposite to that of the what? Opposite the DNA helicase from this side to this side. So that means it will be moving in a 5' with respect to the nucleotide, to the chain which is being added. It will be moving in a 5' to 3' direction. I hope you have understood me. That on the lagging strand, also what happens here is what's happening. The difference is that here we have one primer attaching at the extreme end, and then you add things like this. But on the lagging strand, we have primers at different points. Why is that they got different points? Because we want to ensure the nucleotides, that the DNA polymerase which is going to help us to add these DNA nucleotides onto the lagging strand must flow in a 5', 3' direction. So once the nucleotide attaches itself here, what happens is the DNA polymerase is going to also come starting from the nucleotide, starting from the primer, moving towards in a direction which is opposite that of the helicase moving this side, but the polymerase now is going to be moving this side, moving in a direction which is opposite to that one of DNA helicase, while adding DNA nucleotides which are complementary, following of course the complementary base pairing rule. But we are saying those nucleotides will be added in a 5' to 3' because it's moving in this direction. I hope you are getting. Of course, now this nucleotide will create peptide, will form bonds, will form new bonds with the leading strand, also forming some chains there. Now we are saying DNA polymerase moves along the lagging strand in a direction which is opposite to that of DNA helicase. Doing what? It goes on adding nucleotides, but now since it's moving in opposite direction, we can say it is adding the nucleotides in a 5' to 3' direction, the opposite direction which is moving which is like this. 15, okay. Okay, so what happens because of this? When this polymerase comes and reaches at this point, and this one has been added, and it finds now a what? It finds now a primer here. What it does is that polymerase cannot catalyze the combination of this end with this end here. So what happens is that because of these primers which are here, which are also here, which are here, which are also at different points, what happens is that this leads to formation of chunks or fragments of what? Fragments of DNA. So you will be having, because now this one will catalyze and reach here to find a primer to stop there. Also another one, if you also consider another chain here, remember I have just used only two, but we have very many. So we have another primer, we also have another DNA polymerase catalyzing addition of nucleotides. When it comes and reaches someone finds a primer, it stops there. So we shall have DNA, part of DNA molecule here, and then you shall have a gap because you will have a primer. Then you also have another one. So is reaching is ending at here at the starting point. So because of these primers, what will happen is that we shall have chunks, we shall have segments, we shall have this DNA formed here, then we shall have a gap here. Then we shall also have another DNA here, we shall have a gap here, like that. So because of that, what happens is Yeah, so what happens is that here we end up having chunks of DNA, what you can also call fragments. These chunks you can call them fragments. So fragments of DNA are what? Are formed on the what? On the lagging strand. Why are they being formed? We are forming chunks because we had this DNA polymerase come, and after reaching here, it formed a primer here. Then it also pauses. Then after the same time, we also have this one like that. If this molecule was still adding, we would also having another primer here. So you end up having this capacity, another capacity. So those smaller parts, which with some spaces in between, we are calling them chunks, or we are calling them fragments of the DNA are from the lagging strand. And these chunks are also called, they are also called what? They are called Okazaki fragments. They are called Okazaki fragments. Now, those are chunks of DNA. Why? Because we are saying even when these primers are removed, we are saying this polymerase cannot catalyze the combination or formation of a bond between this carbon, between this 3' and what? And 5'. Remember, we are saying for it must be, so we are saying even when these primers are removed, we are saying the DNA polymerase cannot catalyze the combination of this carbon which is here with this carbon which is going to be with the phosphoric acid which is going to be here. It will not catalyze that formation of that bond. So we are saying because of that, we are going to have a segment here, a chunk of DNA like that. And because of that, chunks of DNA are going to be formed, and we are saying those chunks are called Okazaki fragments. Now, after they have been formed, now we have another molecule. We have another enzyme which is called the DNA what? DNA exonuclease enzyme. Now, this exonuclease enzyme comes and strips off the what? Strips off the primers. So this enzyme, after it comes and removes all these primers, and after these primers are removed, we ensure that everything is matched. And remember, when the primers are removed, we are saying complementary nucleotides which are complementary nucleotides join in. So the complementary DNA nucleotides come and occupy the places where the primers were occupied. But remember, there will be still some spaces. Now, those spaces which are being left, which could not be sealed off by DNA polymerase, or whose sealing could not be catalyzed by DNA polymerase, are later closed up by what we call DNA ligase. So DNA ligase comes and fills up or removes the gaps. Why these gaps are remaining? These gaps are remaining between the Okazaki fragments. So the DNA ligase fills up or removes the gaps which are formed between what? Between the Okazaki fragments. So the DNA ligase comes in, and remember these things would be removed even on this previous one. This one will also be removed on the leading strand. The primer will be removed, and the DNA nucleotide will come and add itself there, join up with the rest. But after that, we are saying for the case of a leading strand, what happens is that after this one has been removed, now the gaps which were removed that could not easily be joined up by the DNA polymerase are later joined up by what you call DNA ligase. And at the end of the day, you end up having your two molecules of DNA when those two molecules are made up, or each molecule is made up of two strands, whereby one strand is the original. For example, this will be the original, and then this one will be the brand new. Even here, you have the original DNA, and then here we'll be having brand new being added there. Yeah, so that's what. So because of what is happening on the lagging strand, we say this lagging strand. Why we say this lagging strand undergo what you call discontinuous replication. Why? Because you see we have replication whereby we end up having some gaps. Then these gaps are filled later by what? Are removed later by the DNA ligase, or their removal is catalyzed by DNA ligase later. But unlike here where things were just combining immediately, and by the time this one reaches the end, everything is done. But here you see, since we have gaps that are supposed to be filled later. That's why we say this lagging strand undergoes what we call discontinuous replication.